Okay, in that case, good evening, everybody, and welcome to Virtual Balticon. This presentation is how to heat and cool your spaceship, or, if you prefer, aerospace thermal engineering. And thermal engineering in space is just like heating and air conditioning on Earth, except that there's no air in space. Everything you use has to be launched by a rocket with limited space and a limited amount of weight carrying capacity. The amount of electricity you use is limited by what's available at the spacecraft, which is usually generated by solar cells. And complicated mechanisms with lots of moving parts are bad because it's hard to repair them when they break. Okay, I'm going to do 3 sections of this talk. The first section is going to be the 3 types of heat flow. The second section is going to be a card demonstration, an exercise that we use where I work, where we introduce some basic concepts and then ask you to help solve a possible problem. Normally we ask the audience to solve it. Don't bother. Chris, don't bother. Okay. But you're off the hook on that one. So, and then we'll discuss some actual spacecraft and their thermal systems and how they work. Okay, the 3 types of heat flow are convection, which is flow of air or fluid, like when you feel cold air from an air conditioner or hot air from a furnace. The second type we'll discuss is radiation, like when you're standing in the hot sun and the sunlight heats you up. And the final one is conduction, like when you touch a hot stovetop or a cold ice cube. Cats have an intuitive understanding of heat flow, so I will use cats to help describe these types of heat flow. Okay, the first type, convection. We're demonstrating convection right here. This little device, let me point the screen down so you can see better. This little device uses the heated air from the candles to drive this little fan, and it turns around and the little angels go around and hit the bells. Okay. This other thing sitting in front of it, this wheel that you see spinning around, that is something called a Stirling cycle engine, which is a very efficient engine that takes heat and turns it into motion. And it's taking the heat that's rising through the air from the hot water in this coffee cup. And the Stirling cycle is so efficient, it's even being talked about as a way of creating electricity in satellites where there is a source of heat. Convection is not just in air, it's in water, it's even in the Earth's mantle. All right, cats, as I was saying, have an intuitive sense of heat transfer. If everything is working correctly, you should be seeing a photo of my cat sitting in front of this thing, which is the grate where the hot air comes out of the furnace, out of the heating system. Now, there's not a lot you can do with convection to get heat into or out of a spacecraft because there's no air out there. And no air out there is why in the Alien movies they said in space, no one can hear you scream. I prefer the kinder, gentler version in Ready, Jet, Go, which is in space there is no sound. However, convection can still be important in a spacecraft if you have fluid flow through pump tubings, like through a heat pipe or through a cooling system that we'll see in the Parker Solar Probe. Okay, the next type of heat flow that we will talk about is radiation. Here is a picture of a cat demonstrating its understanding of heat transfer by radiation. It is lying there in that patch of sunlight that is coming out of the window. Now, radiation just means energy that travels in rays. It can be light rays, It can be radiation from a radioactive element. Light is a kind of electromagnetic radiation. It works by means of electric and magnetic fields that are interacting. Radio waves are another form of electromagnetic radiation, as are infrared waves, which are also called heat rays, because they are detected by the heat they cause in objects that absorb them. You can see them in those thermal cameras that you can get or that they use in the TV programs on CSI. Anything that has any sort of temperature at all radiates. The hotter the thing is, the more energy it radiates and the shorter the wavelength. The sun is like 6,000 degrees Kelvin, and so it radiates really strongly, a lot stronger than we do. And in the visible spectrum, we are much colder. We don't radiate nearly as much, which is a good thing. And we radiate in the infrared region of the spectrum, longer wavelengths, which you can see with those thermal imaging cameras. Even things colder than humans radiate in a way that can be important. Here's a photo of the parking lot where I used to live. You notice that there are trees all along one side. I found out that on cold winter nights when I parked there, the window on whichever end of the car was pointed towards the trees would be frost-free, and the window on the other end, the windscreen, the windshield or the rear window, would be covered with frost. Here's what I think was going on. The car was radiating at really long wavelengths from both ends, but the end that was pointed towards the trees, it was getting radiation back from those trees. The end that was pointed out towards the open sky, well, nothing much was coming back. Pardon me, had to blow out those candles. Now, cats are too smart to experience radiation heating by, for example, putting their paw on a stove or anything hot. So for a cat illustration of radiation heat transfer, I had to use a metaphorical cat. Haven't seen the movie, but that's a dynamite cast. So that is heat by conduction. And I am going to unshare my screen and try to do a couple of little experiments here. Let's see what we can do. Yes, let's get rid of our Stirling cycle engine. And we are going to pour some hot water into this mug. And I have a little classroom demonstration device here with a number of different metals. And on the metals, there are thermometers, liquid crystal thermometers. I'm going to stick the metal bars into the water, and I hope we can see those liquid crystal thermometers indicate the temperature. And you will see that different metals will heat up at different rates because they conduct heat at different rates. Let me see. Let me walk around and see if I can see those thermometers. Oh, I need to be on the other side, don't I? Well, copper is up to 36, and aluminum is down here. There's not much registering on the brass or the steel. The copper is already up to 39,
38, 37,
and 38, 37, 36. 36 is the steel. What we're seeing here, the copper is up to 40. This thing only goes up to 42. This is all Celsius, by the way. What we're seeing here is that some metals conduct heat a lot better than others. Copper, oh, it's up to 41 already. I'm going to pull it out. Copper conducts heat very well. I hope you could actually see that on your screens.
Want me to take that?
I've got another kind of simpler demo here. I have a silver spoon, which I bought on eBay, especially for this demo. I have a stainless steel spoon that I bought from, well, I didn't buy this. It was sitting in our silverware drawer. We call it silverware, even though it's all stainless steel, except for this one spoon I bought on eBay. I've got this heat tube. This looks like a bar of copper, but it's not. It's actually a hollow tube filled with a liquid which evaporates at the hot end, travels as a vapor to the cold end, condenses, and so it transfers the heat that way. I'm going to stick these into that hot water, and we'll see which one heats up first. I know from experience I'm going to have to pull that heat pipe out pretty quickly. Okay, the heat pipe, okay, I'd better pull that out before it gets too hot to handle. So that heated up really quickly. I'm not feeling either. Okay, the silver is starting to get a little warm up at the handle, but the stainless steel is still nice and room temperature. Let's see. Yeah, the stainless steel is getting warm, not nearly as hot as that heat pipe, but it is getting warm enough to feel. And the stainless steel is still room temperature up at the top. So I'm going to end that before we take too much time. Now, the point is, different metals conduct differently. If you wanted to build a system where you had different objects with different temperatures and you wanted to make sure that the heat didn't flow from the hotter to the colder and heat up that colder one, you might make it out of steel, especially stainless steel. If you wanted to build a device to make sure that there was good heat flow from one thing to the other, you might make it out of something like copper or aluminum that has a good heat flow. Okay. So we have done all that. Now we are going to the section where we look at, oh dear, what about different metals makes them conduct heat differently? I would answer live if I knew all the answers to that. The one thing I know is the brass has a lot of different materials in it, so it has a very disordered lattice. Sorry, I'm going to punt on that one. Hope you don't mind, but for our purposes right now, it matters that they do. And I'm sorry, I don't have a good answer for that. Y'all are welcome to ask other questions and stump me just as badly. Okay. Let's look at this. And here we go. I'm going to share my screen again. Share screen. That one. Share. So you all should be seeing a picture of an 8x10 page with design options on it. And up at the top, it says multi-layer insulation. These, on this page, there are 3 tools that we commonly use in aerospace thermal engineering. Multi-layer insulation is a type of insulation. It's like the space blankets that you might get at outdoors stores. They look kind of orangey and silvery, and they work by reflecting heat. The multi-layer insulation is like those, but it has a lot more layers, which is why it's called multi-layer. Most of those layers are made of plastic like Kapton, which has that kind of orangey color, or Mylar. And they have an aluminized coatings on a lot of them. Now, the aluminized coatings look shiny metal like aluminum looks, but you don't usually see that on the outside layer. The reason is, and it has to do with the way shiny metals radiate. A shiny metal is good at reflecting incoming sunlight, and it heats up, but it's not that good at radiating away in the infrared the heat that builds up. Because if you're getting rid of heat by radiation, if you're around room temperature or anything that we would see out of doors, you're radiating in the infrared. And shiny metal just isn't good at radiating in the infrared. White is very good. White is also good at reflecting. So if you have a choice between a white painted car or a silver metal painted car, the white car will not warm up as fast in the sun, but both of them are better than a black painted car, which absorbs sunlight really well. It radiates in the infrared really well, but it absorbs sunlight really well and heats up. Of course, if it's 110 in the shade, your car's not going to be cool for, no matter what color. Okay, so the multi-layer insulation, when the sunlight comes in, it reflects off that first surface, and that sort of cools it down, and then every other surface after that has aluminum coating, which helps reflect the heat back. And the more layers, the better it is at reflecting back. Now, the next thing on that page is a radiator. Remember, I said that white paint was good at radiating in the infrared region, which is what we hope our spacecraft are at, that temperature, more or less room temperature. So we use that to send the heat out. For this little exercise, we're going to say that it absorbs 1/3 of the sunlight that, somebody has posted in the questions a link for why different metals conduct differently. You might want to post that in the chat. You might want to post that in the chat where everybody can see it. There's a lot of information out there, and I used a lot of that for the spacecraft part of this talk later on. Okay, so for our purposes of this exercise, it absorbs 1/3 of the heat that's falling on it and sends out heat to the equivalent of 2 100-watt light bulbs. Now, at the bottom is a heater. You can't see this very well, but if you look closely, you can see that there's sort of a back and forth trace. And that is actually an electric wire. In the rear window of your automobile, there is a trace of wire that goes back and forth, and that heats your rear window and defrosts it. It's the same thing here. Okay, let me see if I can get to our exercise. Yes, here is the exercise. We have a very simple satellite with heat coming in from the sun. Those are the 12 light bulbs equivalent worth of heat. Heat coming in from the Earth. 6 light bulbs equivalent worth of heat. 3 of them are just reflected sunlight, and 3 are the Earth radiating in the infrared. And there's 1 light bulb inside. That's because we have instruments that use electric power and they're turned on. Now, how would we solve the problem of where do we use heaters and where do we use multi-layer insulation, MLI, and where do we use a radiator? Well, let's see about that. As I said, if we were doing this and you were touring students, you would have to come up with the answers yourself, but you're off the hook now. Okay, let me share my screen. That's the one I want to share. Let's go here. Here's a reminder of the tools. The multi-layer insulation. Heat hits it and just bounces back. The radiator. 2 units of heat go out through the radiator. This little rectangle represents a side view of the radiator. Heat that comes in, most of it bounces back, but a third of it comes in. And then we have our little electrical heater that's hooked up to a battery, and it's creating heat. We're restating the problem here. Here's our little satellite with its little solar panels. It's got something turned on inside, which is hot, 1 light bulb's worth. The sun here is giving it 12 light bulbs worth of heat. The Earth is giving it 6. So a total of 19 light bulbs worth of heat coming in. How much is going out? None. Well, it's going to heat up pretty quick because there's a lot of heat coming in and none going back out. The first thing we do is we block the incoming heat with all this multi-layer insulation. So now we've just got that one little box inside, 1 unit of heat being generated, but still there's no heat going out. What do we use to send the heat out? We use a radiator. We put that on. Well, this radiator is so big, it sends out 2 units worth of heat. And we've only got 1 unit worth of heat coming in. So 1 unit of heat in, 2 out. Now we're going to cool off, except that we put a heater inside, which gives us 1 unit worth of heat to add to the 1 unit of the box. And so in is 2 units worth of heat, out is 2 units worth of heat. It balances. Our spacecraft is going to stay at its same temperature, which is good, because if things get too hot, they break. If things get too cold, they break. For example, I wouldn't put your phone in a pizza oven. A pizza oven is really great for a pizza, but is not a good place for a phone. Please do not try that at home. Okay, we are going to quit that. Now we are going to the part of the talk where we talk about actual spacecraft. The first spacecraft I'm going to talk about is the Lunar Reconnaissance Orbiter. Share screen again. Preview. Lunar Reconnaissance Orbiter. Share. You should be able to see this big picture of a spacecraft. Are we seeing it? I hope so. Your screen is sharing. Yes. This goes round the moon. It takes a couple of hours to go round the moon. It's usually roughly 1 hour in sunlight, 1 hour in shadow. And they've designed it to be big enough so that it doesn't cool down that much in the 1 hour in shadow, doesn't heat up that much in the 1 hour in sunlight. And it's got some batteries, so if it cools down when it's in shadow, it can turn on the heaters. And it's designed for 1 hour, 1 hour. Okay, that's cool. Except when we have lunar eclipses, which can last for like 3 or 4 hours. It's designed so that it barely makes it, even if they pull every trick they can. Now, they could have put a whole bunch more batteries on it. Well, I should remind you that when it's in shadow, the solar panels aren't working. So anything electrical that happens to happen from its batteries that get charged up when it's in the sun. They could have put really big batteries to keep it nice and toasty warm when it's during a solar eclipse, and not a solar eclipse, a lunar eclipse, when it's in a lunar eclipse. But those would be very heavy and they would take weight allowance away from the instruments that the scientists put in there, because the whole purpose is to have these cameras and things that are studying the moon. So it just barely makes it by design. All right, enough of that. Next, we are going to Messenger, which is a spacecraft that orbited Mercury. It was the first spacecraft to orbit Mercury. It was the second spacecraft to actually get to Mercury. Okay, I hope you are now seeing a drawing of the Messenger spacecraft. You know, I have to get my notes so that I remember what MESSENGER stands for. Mercury Surface Space Environment Geochemistry and Ranging, but that will not be on the final. Okay, here's an overall drawing of the spacecraft. And I will use that to illustrate why it is so thermally challenging to orbit Mercury, because you are close to the sun. And Mercury's orbit, it's a little bit elliptical. When it's farthest from the sunlight is like 4.6 times as strong as it is here on Earth. When it's closest, it's like 11 times stronger than it is here on Earth, and the spacecraft has to survive that. But the sunlight is only part of the problem. You've also got infrared radiation, that heat radiation from Mercury. Now, on a hot summer day, when you stand outside by a concrete sidewalk, you can feel the heat radiating off that concrete sidewalk. Well, imagine if that sidewalk were on Mercury and it were getting 11 times as much sunlight as it would get here on Earth. So Mercury is kind of baked by the sun on one side, and when it's flying in between the sun and Mercury, it's also baked by Mercury on the backside. In fact, if you were standing on the part of Mercury which is right under the sun, where the sun is right overhead, on a cold day when we're farthest from the sun, the temperature would be 300 Celsius or 570 Fahrenheit. On a hot day when we're close to the sun, the temperature would be 430 Celsius or 800 Fahrenheit. Now, on the dark side of Mercury, it's a comfortable minus 180 Celsius or minus 300 Fahrenheit. So that sun shield always faces the sun, or the spacecraft is going to fry. So when it flies, but the spacecraft has to fly past the sunlit side of Mercury so its cameras can take pictures of Mercury. So to take any data at all, it has to fly right in between. So it's got hot Mercury on one side, hot sun on the other side. Here's a photograph of the sun shield. It's that big, tall, white thing. It's made of something called ceramic cloth. You can see a guy in the background in one of those bunny suits that you have to wear in clean rooms. For a little bit of scale, there are few things on the sunlit side of the sun shield. Some thrusters, because you got to have maneuvering thrusters on all sides of your spacecraft to point it any direction, and some antennas, which for some reason couldn't be on the cold side and still see what they needed to see and be able to send signals back to Earth. Okay, now the orbit of MESSENGER is part of its thermal system. It spends about 30 minutes passing between Mercury and the sun and getting heated up. Then for 12 hours, for the rest of the 12 hours of its orbit when it first started, or 8 hours towards the end of the mission, it gets away from Mercury so it can cool off. And they also designed its orbit so that when Mercury is closest to the sun, it doesn't fly directly over that hottest point on Mercury, which is right under the sun. Now, there's also another thing they do. They use diode heat pipes. Remember I showed you that heat pipe? I stuck it in the hot water and I could feel it getting hot really quickly. Well, they use heat pipes to take heat from the instruments, which are, electrical equipment, so the electronics heats up, out to the radiators to radiate them away from the spacecraft. But when you're passing directly over really hot surface of Mercury, those radiators are getting all this infrared in, and they're getting pretty hot. So the diode heat pipe is a type of heat pipe that automatically turns off when the end that is supposed to be connected to the radiator, this end that's supposed to be cold, gets hotter than the hot end, the end that's connected to the hot electronics box. And we'll use an old phrase: the explanation of this phenomenon is beyond the scope of this presentation. Okay, it's magic, basically, if you remember Clark's law. So That is Mercury and the Messenger mission to Mercury. And by the way, when it was really far from the sun, early in the mission, they actually turned it so that the sun shield was away from the sun so that the sun could help keep the instruments from freezing. That was when it was like almost out at the same distance from the sun as we are here on Earth. Stop screen sharing. Now I am going to talk about the Parker Solar Probe. That's the spacecraft that is now flying through the outer atmosphere of the sun. It's named after a scientist, the guy who invented the term solar wind. I'm thinking that most of you who are interested in the sun and solar physics probably know about the solar wind. It's one of those terms that you think was always there, but in fact, it had to be invented by somebody, and this guy named Parker invented it. Here's a picture of the Parker Solar Probe. This is their mission emblem, and you can see it right up close to the sun. Here's a diagram. Yes, there's a thermal protection system, basically a heat shield. Next to that is the solar array cooling system. These are radiators, but they're black because they're never going to see the sun. We certainly hope so. Black is just as good as white for radiating heat away. Here are the solar array wings. These are the solar cells here to get to generate the electric power. Now we're going to talk about this thermal protection system, this big slab here that the edge looks black, but it's not all black. This is a picture of a sample of the material that heat shield is made of. The interior part of it is a carbon foam, which is 97% empty space. And on front and back, to help it stay together, it's got carbon-carbon composites. These are like the carbon composite material that some fancy tennis rackets and golf clubs are made of, or even cellos and guitars. Okay. They love demonstrating this stuff. This probe is made at the Johns Hopkins University's Applied Physics Lab. The same is true of Messenger. That was made by the Applied Physics Lab of the Johns Hopkins University. Here we see two people and a block of the foam. Let's see. The person with the blowtorch here is Betsy Congdon, lead heat shield engineer. And the other person is Jim Kinnison, Parker Mission System Engineer. In other words, somebody they really don't want to get rid of. So he's touching the side of this block that is opposite from where Betsy is heating it with the blowtorch. And he is saying, well, this isn't very hot at all, which it's not. Here is a close-up picture. They like doing this demo. This is actually Curtis Wilkerson's hands on another video that you can find online. And again, Curtis is saying, this stuff is really not that hot. Now, in the first demo, we saw this big device in the background, this shiny metal framework and this big black and white thing. Well, here's a close-up of it. The shiny metal is made of tungsten, and that's a metal that has very low thermal conductivity. And that's what you want as a framework to hold that heat shield, which is exposed directly to the sun. And as we see, the top of the heat shield is painted white so that it will reflect the energy and only absorb some of it, and the rest of it, this heat shield is very good at stopping it from getting through. Here's a diagram, another diagram. This is a picture of the spacecraft, and you can see the heat shield over here on the left end of that diagram with the cutaway layers, and over on the right hand is a cross-section of the heat shield with its white ceramic coating on top. a barrier to keep the ceramic coating from mixing with the carbon, which for some reason it would do, and then sandwich the carbon foam between two layers of carbon-carbon. Now, why wouldn't the solar corona heat up the spacecraft and melt it? Well, it's because the solar corona is almost a good vacuum. In fact, as dense as it is, it would make a decent laboratory vacuum. And remember, vacuum is what insulates a thermos bottle, so it's actually good insulation. Even though it is hotter than the surface of the sun than we see, it's so dim you can only see it in an eclipse, which is a great thing to do. Go to totality when that next one comes up. When is it? 2024, I think. It's an amazing sight that you'll be glad you went to see. You can't see it from any place where it's just a partial eclipse. But that's why the Parker Solar Probe doesn't melt from the heat of the corona, but it's so close to the sun, it's over 475 times the sunlight is as strong that it sees as we see here on Earth. So it really needs protection from that hot sunlight. Now, just like MESSENGER, it has a very elongated orbit, as you can see in this diagram here. And when it's at the perihelion that is closest to the sun, you can see it here. And for about 11 days, it swings by the sun, and it's really close, and it takes science data. And then for like 158 days, it swings out here and it cools off, and it takes all the data that it collected and it radios that back to Earth. Notice from this diagram, you can see that the sun shield is always pointing directly at the sun, and that's done internally, autonomously. Now, down here is a thing about solar array position. What that means is when the leftmost image, that shows the way the solar wings come swinging in when it's right close to the sun to keep them from overheating. And because the sunlight is so strong, it only needs the tiny little tips of those solar wings to get enough sunlight to generate all the electricity that it needs. And then when it goes farther from the sun, the wings swing out a little bit in that middle picture, and then when it's way out, like out the same distance as the Earth or Venus or whatever, you can see that the solar wings swing all the way out so that in the sunlight that's out here, it still has enough electricity. Here's a picture, artist's conception of it swinging near the sun. You can see that these solar panels are really pulled in. Somebody's asking a question about graphene. Isn't it a good conductor of heat? Well, the reason the reason that the carbon foam is a good insulator is because there's not much of it. It's like 97% empty space. Now, graphene, I don't know a lot about graphene, but I know it's a particular molecular structure, the same as you get in graphite, which is the thing that they call the lead in a pencil. I don't know what the molecular structure would be in that carbon foam, but because it's mostly empty space, it's 97% empty space, it's almost as good an insulator as a vacuum. So that's the reason why it's a good insulator. It's not the carbon itself, it's the empty spaces between the carbon. Okay, a question I could sort of answer. Thank you. Here's a picture showing artist's conception of the Parker Solar Probe when it was near the Earth, and it had to swing those solar panels way out so that they were completely exposed so that it could generate enough electricity. I'm not sure how well you can see the details on this picture, but it's a simulation of the orbit of the Parker Solar Probe. This is done by the Scientific Visualization Studio at the Goddard Space Flight Center. They take scientific data and turn it into videos. They are really good. I know of at least one person who has worked both there and at Pixar. This is a screenshot from a particular video. Here we see the orbit of the Parker Solar Probe going around the sun. This is the sort of greenish blue line, which turns to red when it's here, when it's close enough that it can take data. And out here, this yellow orbit is Venus. So the Parker Solar Probe goes as far out as Venus. It gets really far away from the sun, so it can really cool off. Great video. You can really see how the Parker Solar Probe swings really fast past the sun when it gets in close. As we know, the closer you get in your orbit to the sun, the faster you're going. Look up the Scientific Visualization Studio at the Goddard Space Flight Center. Great videos there. Part of the thermal system of the Parker Solar Probe is its autonomous guiding system. If the angle that it's facing the sun got a little bit off and sunlight got past that thermal shield, it would fry everything it touched. Remember, 475 times as strong as the sun is at the Earth. Those little circles represent sensors that are watching to see if any sunlight gets past the edge of the heat shield, the sunshade. And if any sunlight hits them, they immediately tell the Parker Solar Probe's computer, and it adjusts the attitude so that it is once again shielding the spacecraft from the sun with that solar probe. Now, there's actually water on the Parker Solar Probe. The solar array panels are cooled with water. The water goes through tubes, and then it runs up to that black sort of conical section that is right behind the heat shield. Let's go to the drawing again. You see this section called the solar array cooling system. Water is piped from the solar array wings, the solar panels where the solar cells are, up to this cooling system where it radiates its heat back away, and then it's pumped back to the solar array wings. Now, the crazy thing is, they actually had to have a heater on the water tank because there's a point during the launch when it would get so cold it would freeze. So it goes from freezing temperature to right in next to the sun. Very challenging job to design that thermal system. Okay, we've got a little time left. I can go ahead and talk about New Horizons, the spacecraft that visited Pluto. Now, there was a challenge. It had to survive in the inner solar system where things are relatively warm. And then it had to go way out past Pluto. We should be seeing New Horizons, an artist's conception of the New Horizons. Notice that it's all covered with that MLI, that gold MLI stuff, so that it won't cool off too much, except for the interior of the big dish antenna, because MLI, multi-layer insulation, has aluminum in it. 5-minute warning. I think we'll make it. Okay. Stop share. Share screen. Here we go. And share. Here's a little picture. This black thing sticking out to the side, that's a radioisotope thermoelectric generator. Plutonium isotopes, which are radioactive, which thereby generate heat, that heat is turned into electricity. And you need that if you're out by Pluto because there's so little sunlight. And notice that even the back of the big dish antenna is covered with MLI because they need that when they go way out far into the solar system. But then when they're in close to the solar system, they've got more heat than they need. They have various devices. For example, things called louvers, which look like Venetian blinds. They open up when it gets too hot inside and allow the heat to radiate out. On this drawing, you can see the louvers are on, yes, here is one set of louvers, here is another set of louvers. Here is something called a shunt panel. When they've got more electricity from this radioisotope thermoelectric generator than they need, they can use the electricity, just run it through a resistor and then radiate out the heat. And these RTGs, you can't turn them off unless you can find a way to turn off radioactivity, which doesn't work very well. All right, we've only got a couple minutes more. How does the Stirling engine work? I'm sorry, you asked the other question that I couldn't answer. Every so often I go and read up on that. I'm pretty sure Wikipedia will tell you, but I'll give you a quick introduction. Suppose you had a cylinder with a piston in it. You could make the piston go back and forth by first pushing heat in and expanding the gas and pushing the piston out, and then cooling it down and pulling it back. And then you'd have to add a whole bunch more heat and push the piston out and cool it down and pull the piston back. But that would waste a lot of heat. You're putting heat in and then pulling the heat out to cool it. This system uses a device which stores the heat in between times. And that's how it does it. Instead of heating everything up and pushing the piston back and then cooling everything down and causing the gas to contract and pull back that piston, it takes that heat that is pulling out and stores it in something. Okay. Well, I've got my 2-minute warning. I think that's it. Thank you all for attending. There is a Discord page that Balticon has set up. You probably see some links on that, and you can go there and talk about things further. Good night. Hope you enjoyed it and learned something.